Okay, so yesterday we started talking about universal wave equation, okay, and the universal wave equation we wrote out, okay, it looks like this. Okay, V equals F times lambda. Which one of those three properties about a wave can't change once it's produced? Frequency. Okay, so what that means is then that if the speed of the wave changes, the wavelength also has to change in response to that in order to maintain the frequency of the wave. All right, what controls the speed of a wave? The medium in which it is traveling. So if I change media, or I change any property of the medium I'm currently traveling in, then I'm going to see a change in both speed and wavelength of a wave. Just like as waves approach the shore, okay, they slow down, they get shorter, taller, okay, and as a result, okay, we see them differently. All right, everybody okay with that? Okay, so we're going to go over how the universal wave equation works and some kind of simple problem solving that goes along with it, okay, because well, this is a pretty simple formula. So the tricks all come in the context of the questions, okay, rather than in the difficulty of the mathematics, okay, because, well, there isn't any. Okay, this is a pretty easy formula. This is essentially V equals D over T for waves, because, well, when you change this to this, it's literally D over T, okay, meters over seconds. All right, in case you need to see the rest of that cartoon. You definitely wouldn't want to put those two places next door to each other. It's pretty funny. Yeah, Glenn Larson's fine. He's fine. All right, so if we wanted to calculate how fast a wave was moving, right, there's a number of ways to do that. I could just measure out a distance and time how long it takes the wave to travel through that distance, but that's not really practical out in the middle of the ocean. Okay, it's kind of hard to put markers out there and not have them move around and stuff like that. So we're better off to try and use the properties of the wave. Okay, I can count very easily how many waves go by me in a certain time interval and get their frequency. Okay, I can use things like a boat if I'm out on the water. Okay, if I know the length of the boat, I can figure out the wavelength of the waves just by comparing how many of them fit under the boat. Okay, things like that. Right? Those are easier things to measure about a wave than to try and time it as it travels, especially if we're talking about a sound wave, which is invisible. Okay, we can hear it, but it's pretty hard to, do accurate timing with sound. Okay? It travels, I mean, for a wave, fairly slow, but for us, in terms of reaction time, pretty fast. Okay? Even if you're, like out at a track meet or whatever, okay, and the gun is on the far side of the track, you see the smoke well before you hear the sound of the shot. Okay? All right, so how fast does a traveling wave move? Well, we can measure how far the wave travels in a set time interval and use V equals D over T. That's definitely one way, okay? Or we could understand that the speed of the wave is dependent on the properties of the medium in which it is traveling. So when we have a situation like this, okay, we've got our waves out in the deep ocean, okay, and as they approach the shore and the depth decreases, especially once it gets to about half the wavelength, we start to see shallow water waves appearing, okay, where the waves are getting shorter, taller, and tending to curl more, okay, and giving us kind of those breaking waves. And then once we get into about 1/20th of the wavelength as the depth, they kind of just peter out, and we see that kind of back and forth movement of the water near the shore, okay, which is kind of like simple harmonic motion, right? We just see it kind of oscillating back and forth. Oops. All right, so the universal wave equation works like this. V is lambda, wavelength, divided by period, or F times lambda. This is the more common way to see it written. Okay, what are the units for frequency?
Hertz.
Hertz, okay, and hertz means per second. So when I multiply per second by meters, I get meters per second. So I still get speed, okay? When I use this formula, I divide meters by seconds, because seconds are the units per period, and I get meters per second one way or the other. Doesn't matter which form I use, okay? All right, everybody okay with that? That's the stuff we covered yesterday. All right, so a very, very simple, okay, kind of question about this would be, I give you the frequency, I tell you the wavelength, and I ask you to calculate the speed. I probably won't do that on a test because that's like really, really beneath you. All right, like you should, if I ask a question like that, feel insulted. Okay, like it's that much beneath you. All right, so if I want to calculate that, I just take lambda and multiply by the frequency. I get 338 meters per second. That's a pretty reasonable rate of speed for a sound wave to travel in air that's, about 5 degrees or so. Okay, maybe 10 degrees, something like that. Okay. Does the temperature of the air affect the speed at which sound travels? Because it's a property of the medium. Okay, the warmer the air, the faster the sound will travel. Okay, so at 0, it's about 332 meters per second. Okay. And in fact, there's a formula that calculates it. It is 332 plus 0.6 times T, and this T stands for temperature. Okay, so if you're ever given a question and it tells you the temperature of the air and it's about sound, it's giving you the temperature so you can calculate the speed of sound. Okay, and this is the formula you would use to do that. It is on your formula sheet. Okay, 332 plus 0.6 T. Okay, that temperature needs to be in degrees Celsius. Right? If it's in Kelvin, this formula doesn't work. Right? But if it's in Celsius, then you've got positives and negatives, and if you go down below 0, it's smaller and smaller because you're adding a negative number. Okay, everybody all right with that? It's an easy formula to use. You're never going to have to manipulate it. You're only ever going to use it to calculate the speed of sound in air. All right, so we're going to look at a couple of examples here. I want you guys to write this one down and calculate it. Okay, and I know I just told you if I ever gave you information, ask you to calculate speed, feel insulted. This one's not one that should make you feel insulted because there's a trick in this one. All right, so I'll give you a few minutes to write that one down and give it a try. How many waves are there in this question? 5. That's the trick. Okay, let me diagram it out for you. So it says they count 6 crests. Okay, so there's 1 crest, 2 crests, 3 crests, 4 crests, 5, 6. Here's where they start counting. First crest. That's 1 complete cycle, 2 complete cycles, 3 complete cycles, 4 complete cycles, 5 complete cycles. Okay, there might be 6 crests, but there's only 5 wavelengths going by because we don't count, like the first crest is like 0, right? And then we go from there. That's where we start counting. So anytime a question tells you this many crests or this many troughs go by, the number of wavelengths is always 1 less than that number because a wave has to be a full cycle in order to be considered 1 wavelength. Okay, does everyone follow me on that? Okay, so that's the trick with this question. Okay, so in 30 seconds, 6 crests go by. Well, that means in 30 seconds, 5 waves go by. So that tells me that the period, okay, is going to be 30 over 5. Okay, which means the period is 6 seconds. Okay, the distance between the crests is 4.5 meters. So they told me the wavelength. Okay, what's the speed of the wave? Well, v equals lambda over t, because that's what I have. Okay, 4.5 over 6. Okay, gives me a very different number than 4.5 over 5. Okay, because that's what we would have got if we just said there were 6 wavelengths instead of 5. Okay, everybody follow me on that one? Kind of a trick, right? It's a dirty trick, but it's kind of a trick. And we have to remember that when we're talking about the number of crests, it's not the same as the number of full wavelengths. Okay. Can I move on to the next one? Okay. Write this one down and try it. Spoiler alert, it also has a trick. Okay. First thing I got to do in this question is use that formula I just showed you guys that calculates the speed of sound in air at various temperatures. So 332 plus 0.6 times 22 degrees, okay, is going to give me the speed of sound there. So 332 plus 0.6 times 22. All right, 345.2 meters per second is the speed of sound. Okay, so now, person yells at the cliff and they hear the echo 3.5 seconds later. Do I need the universal wave equation for this question? I don't. Okay, there's absolutely no reason for me to use universal wave equation here because, as the note said earlier, I can still use this if I have the right information. And I do. I have the time and I have the speed. Okay, now I want to calculate how far it is to the cliff. How far did the sound travel? There and back again. Okay, so either you use 3.5 seconds and divide your distance by 2 because you calculated the distance there and back, or you recognize that this is an echo and it travels there and back and you divide the time by 2 before you even start. Okay, because it only takes half that much time to get to the cliff. Okay, this is the trick with echo questions. People forget it all the time. Okay, whenever I give an echo question, that could be like using sonar to figure out how deep the ocean is. That's still an echo. Okay, we're still waiting for the sound to go all the way down and all the way back. Okay, so in an echo question, I would simply alter this to go D equals 345.2 times whatever, that's 3.5, right? So that's going to be 1.75 seconds. Okay, get half of that. All right, so the cliff is 604 meters away. Actually, we only have 2 significant digits, so 6.0 times 10 to the 2 meters away. So like I said, there's no mathematical challenges to these questions. They're incredibly simple mathematically, but there's contextual tricks that we have to watch out for. Okay. Anybody need that one anymore? No. Okay, I like number 3 though. We're going to do number 3. Okay, number 2 is just like the question we just did, so we're not going to bother doing that one. But I want you to try number 3. Okay, so a fisherman anchors his dinghy in a lake 250 meters from shore. The dinghy rises and falls 8 times per minute. Okay, and he finds that it takes 3 minutes for the wave to reach the shore. Okay, how far apart are the wave crests? Right. So if they're asking you how far apart the wave crests are, what are they actually asking you to calculate? The wavelength. Okay. Now they do give you some other information in there that can help you find other parts of the universal wave equation. So I'll give you a couple minutes on that one. Okay, how many people converted the minutes to seconds? Okay, and it's fine if you did, but you actually didn't have to, because we were given the time in minutes, and we were also given the frequency in cycles per minute. So we could have actually left it in minutes and avoided one calculation. If you convert it to seconds, it's not a big deal. Okay, I'm just going to save myself time and not do that. Okay, and I'm going to get the same answer here. So I want to calculate the speed of the waves. I'm going to go 250 meters divided by 3 minutes, okay, to get my speed in meters per minute, which is a ridiculous set of units to have it in, but for this question it will work. Okay, 83.3 meters per minute. Okay, and then I'm going to calculate the frequency because I know it goes up and down 8 times per minute, so that's going to be 8 cycles per minute. Okay, and now I can go V equals F times lambda, okay, and I will get the wavelength. So I'm going to divide both sides by frequency, okay, and I'm going to have my meters per minute divided by cycles per minute, okay, and that's going to leave me with meters per cycle, which is okay, that's wavelength. Okay. So we're going to take our 83.3 and divide that by 8, and that's going to give us 10 meters for the wavelength.
Would it be 7? Like, because it says it rises and falls 8 times.
Rises and falls. So that's a complete cycle, right? So it rose and fell 8 times. So I get where you're coming from, right? You were saying, well, Codere, when you said it's 6 crests, it's actually only 5 cycles. You're right. But in this case, because it's specified that he went up and down 8 times, that's actually 8 full cycles.
Okay.
If they said he went over 8 crests, you'd be absolutely right, and there would only be 7 wavelengths. Yeah? Okay, questions on that one? Okay, are there lots of little weird tricks here? There's lots of them. It's just a matter, these ones, that's what you have to watch for. Read the context of the question really, really carefully. Okay. Okay, I want you guys to try that one. Okay, so we got 2 tuning forks, they're identical. They're both making a frequency of 384 hertz. Okay, the waves from one tuning fork are generated in air, where the speed of sound is 350 meters per second, and the other tuning fork is generating sound underwater. We're going to ignore the fact that tuning forks really don't work very well underwater. Okay, because, well, they don't vibrate all that well underwater. But we'll ignore that fact. Okay, where the speed of sound is 1500 meters per second. Calculate the wavelength for the sound in air, the wavelength for the sound in water, and part C, would you hear the same musical note underwater as you did in air? Can we answer part C right now?
Yes.
Would I hear the same frequency?
Yes.
Yes. Okay, because frequency never changes, and the tone, the same musical note, that's because of the frequency, okay, above and below, it's 384 hertz. Okay, it's the same tuning fork. I'm not going to hear anything different. Okay, try A and B. Okay, so is this one just 2 universal wave equation calculations manipulated for lambda?
Mm-hmm.
Yeah, okay, so we got for air, okay, lambda in air is going to be our V, which was 350, divided by our frequency, 384, okay. Okay, so we're looking at 0.91 meters. Right, we got a lower speed and a lower wavelength. Okay, lambda in water is going to be still V over lambda, but now it's 1500, or sorry, V over F, 1500 divided by 384. Right, we got a higher speed, so we got to have a longer wavelength.
So the faster the wave is going, the longer the length of the
Yep, absolutely. Yep. All right, we have 3.9 meter long waves in the water. Okay, because if we had a speaker up above the water playing music, when that wave hits the water, the wave speeds up, right? But the back of the wave is still in the air, we're traveling slower, so the front of the wave runs away from the back of the wave and gets longer. Okay, making sense? That's actually called refraction, which is something we'll go over when we talk about wave behavior later. Not today. All right, in the digital workbook, there are some questions that I want you to try, all on universal wave equation, but I'll tell you which ones because I don't think we need to do them all. I think that would be overkill. Okay, so something that, sorry, this hasn't come up yet, but just in case it, well, and it's going to on here. Radio waves. How fast do radio waves travel? Speed of light. Okay, so anytime you have an electromagnetic wave, a light wave, a radio wave, a microwave, anything that's light, the speed of the waves is the the speed of light, which is under other useful constants on your formula sheet. It is 3.00 times 10 to the 8 meters per second. So sometimes a question like number 3 will say a radio wave, a form of electromagnetic wave, has this frequency. And for light waves, you're often going to be given the frequency in megahertz. Okay, remember, a megahertz is 1,000,000 hertz. Okay, so if it's 99.5 megahertz, that's 9.95 times 10 to the 7 hertz. Okay, so it's big. Okay. And then we got our question about triple tanks. If you use the sound waves, then you got to go with the speed of sound as calculated with that other formula that we talked about as well. Okay. I would like you guys to do and okay, I want you to do 12, 21, and 18. So 12, 18, and 21 on the in the digital workbook there. Okay, so let's have a look at this one. So 2 men are fishing from small boats, and the boats are 30 meters apart. Waves pass through the water, and each man's boat bobs up and down 15 times. How many cycles is that? 15, because it actually said that it went up and down. That's the key thing, right? It said it completed 15 full cycles, okay? And it did that in 1 minute. So I'm going to go 15 over 60 to get my cycles per second, or frequency. Okay, so that's the first thing I've got to do with that. Okay, I'm going to go 15 divided by 60, right? I can't believe I did that. 0.25 hertz. Okay, is my frequency there. Now, the boats are 30 meters apart, and at one time, when one boat is on a crest, the other is in a trough, and there's a crest between the two boats. I got to draw a picture. Okay, that just starts to make my mind go crazy. All right, so there. All right, that should do it. So when one boat is on a crest, the other is in a trough, and there's a crest in between them, and that distance is 30 meters. How many waves is it? 1.5. Okay, because from here to here is one complete cycle, and to there is another half a cycle. So I know that 30 meters equals 1.5 wavelengths. So if I divide 30 by 1.5, I'll get the wavelength. All right, so I got 20, okay, and if I want to figure out now, sorry, my wavelength is 20 meters. If I want to find the speed of the wave, v equals f times lambda, okay, and so that'll be 0.25 times 20, which is 5.0 meters per second, okay? It's all word tricks, right? I mean, the way these problems get tricky is by trying to trick you with words, okay? So words can hurt. Okay? Remember that, it's a life lesson. Okay? So yeah, it's just what it is. But so just make sure you're reading the question carefully. Something like that just takes a little diagram to get it figured out. Okay, and you guys can do that. All right, on Monday we'll be continuing on with waves. Probably moving on to wave behavior at a boundary. Okay, then we'll be looking at interference. And then we'll probably run out of time, and we'll get to go home for 2 weeks, which will be nice. I'll miss you guys. So, yeah, it'll be nice for sure. Yeah. Just gotta say, it's like.